Welcome again to Let's Talk Advanced Chemistry, Chemistry 2 with Pastor Dan. We're looking today at a phenomenon involving weak acids and like ion salts involving something called buffers. Now, buffers are solutions that are resistant to change in pH. And so we're going to determine how we identify what acid we use in order to make a buffer at a specific level. pHs are designed to hold at a specific amount so that way they don't change. We talked about it last year, and now we're just going to talk about how we create those specifically. Now we do that, something called the common ion effect. Common ion effect is a means of affecting the process of dissociation by increasing the concentration of both ends of an acid with a like ion salt. So if we have a generic acid, we're going to consider that weak, so it's in equilibrium. We're going to generate our hydrogen ion and our anion. Now, when we take the light ionized salt, we have to make sure that that dissociates 100%. What that does is that's going to make the concentration of my anion blow up. According to Le Chatelier's principle, when this blows up, it's going to push the reaction, and the hydrogen ion is going to become even less, and then the acid. So we're going to have a massive amount of acid and a massive amount of ion. So whenever the hydrogen ion shows up, the anion is going to attack it, form the acid. When the hydroxide shows up, the acid is going to attack it and form water. So therefore, that keeps hydrogen or hydroxide in. It's not going to affect the pH. Now, the way that we do this is through derivation. So here's my acid dissociation. If I do my Ka is going to the products over the reactants. And then what we're going to do is going to rearrange the sulfur for a hydrogen ion. Bring hydrogen ion, rearrange it. So we're going to bring the X down and the acid up. We then say, okay, if I take the negative log of both sides, I have a negative log of hydrogen ion, which we know is going to give us our pH. And the negative log of the Ka times the negative log of the acid. Now, we take that, and we know that when we are going to divide something through, when we're multiplying through, we can separate our terms. So we have a log of Ka, take a log out of each of those, so log of Ka minus a log of the anion. Now, if we take the negative log of hydrogen ion, that's pH. Negative log of the Ka is something called pKa. So we're just going to make it a number. And then we have the negative log of hydrogen ion, the acid over the anion. Now, we consider that the acid and the base, okay, because the anion is the base. And then if we flip those, we can get it from being negative to positive. So the final equation we're going to use to find pH of buffers is pH is equal to pKa plus a log of the base over the acid. All right, so let's take a look at an example. Determine the pH of 7.655 molar acetic acid. And over here, I have the acid Ka value, so we can find those. So acetic acid is right over here, 1.8 times 10 to the minus fifth. So we plug our values in. So the pH is the negative log of Ka. That's how we find pKa. Acetic acid, we said is negative 1.8 times 10 to the minus fifth. So when we do that, we get 4.745. Now, for our acid, for our reactions, the anion is my base, the acid is the acid. So we're going to have a log of 5.559 acetic acid over 7.7655. Now, you take a calculator, take log of 0.5559, divide by 0.7655, close parentheses, equal, and we get an answer of negative 0.1389. If it's less than 1 log, we're going to get negative value. Add those together, last for the column. And I just always do 4 sig figs over here because, well, right here we have 4 sig figs, but in reality, this is definitely significant for my problem. So going off of here, that'll give us our 4 sig figs. That's what we're going to use. Answer then is 4.606. That would be the pH of solutions. Okay, we're using 4 sig figs because of the 2 values inside of there. When we do last fill column, tenths, hundredth, thousandth place, we're going to cut it off at 3 values. It's a little bit clearer understanding there. The solution will hold right at 4.606 until the buffer could be exceeded, so it keeps it relatively regulated specifically at that. So use a specific acid with specific concentrations of acid and anion to create a pH that you desire. All right, let's try another one. Okay, now I'm going to pause I want you to pause the video, copy this down. Try this one on your own, exactly the same. So what you're going to do is, using the equation, identify, and losing the chart over here, chlorous acid's right here, 1.1 times 10 to the minus 2. So work through this. Any question, remember ltswpd@gmail.com. Remember, like, subscribe, share. Any questions, let me know. Comment, I will try to respond back. Okay? Identify let me fix this. There we go. Identify the pH of 1.988 molar chlorous acid with 2.005 molar sodium chlorite. Chlorous acid is right here. It's 1.1 times 10 to the minus 2. So we show all the work there. All right, that's how we do that. No problem. All right. Okay, so pause, look at it. It's pretty straightforward, not too difficult. Now, what I want you to do now then is pause the video, work through these. I'm only going to give the answers. All your values are right here for all of them here. Hypoiotis is in there. Boronate, we use the first protonation. And we want to identify the acid. So what you're going to have to do is find the pKa. Now, all you have to do there is take the value for the pH and then take your logs and subtract it. That'll give the pKa. The inverse log of that, the anti-log, will give us the Ka value. All right? So, ready? Here are the answers. All right. So we have 9.277. We have 10.35. And the pKa is 7.295 times 10 minus 5th, which would be 7.3 times 10 minus 5th, and that's benzoic acid. All right, hopefully not too bad. Take care. God bless. Bye.